Welcome to this week's Crunch seminar. Our first speaker today is Roberto Molinaro. He's currently a PhD student with Professor Siddharth Mishra, and he has completed his master's degree at ETH Zurich in the Department of Mechanical Engineering. His research focuses on scientific machine learning, specifically on applying physics-informed neural networks for forward and inverse problems. In particular, he's interested in high-dimensional PDEs and exploring how pins can improve the resolution of such equations. Recently, he has also ventured into the field of operator learning and its potential applications for learning operators for the underlying PDEs. With that, please join me in welcoming him for today's presentation. You may want to take it away.
Thanks a lot, Samantha, for your kind introduction. And also, thank you very much for inviting me. It's a real pleasure. And what I'm going to talk about today is neural inverse operators for solving PDE inverse problems. But before delving into it, I would like to acknowledge the people I work with, particularly Yunan, Bjorn, and my supervisor, Sid, that probably many of you know. And I would like to spend a couple of minutes talking about inverse problems and what means solving inverse problems. So let's consider a generic forward operator, F, which can be linear or non-linear, between two different normal spaces. And now, solving an inverse problems consists in finding, if exists, a state A such that f of A is equal to U, where U is the observable, so what we actually measure. And given the measurements of U, we would like to infer the underlying state A. And for instance, in the context of partial differential equation, the forward operator might be the operator which takes as input the coefficient of a coefficient in the partial differential equation and returns the solution of the PDE. For instance, in the case of the ET equation, the forward operator can be the operator which takes as input the diffusivity A and returns the solution U, which corresponds to the temperature of the medium. And then the inverse problem might be, for instance, given measurements of the temperature U, infer the underlying conductivity of the medium. And the main question that naturally arises when solving inverse problem is, can we actually reconstruct in a stable way the underlying coefficient A? Or in other words, if we are given two observables which are very close to each other, let's say U and U prime, this is also true that the corresponding states A and A prime are also close to each other. And this is known as stability of the inverse problem. And unfortunately, the bad news is that most inverse problems are ill-posed. So this means that even though two observables are very close to each other, the corresponding states can be very, very different. And this is what makes inverse problems ill-posed. And now I would like to give you some examples of inverse problems. The first one is electrical impedance tomography. This is widely used in the medical field. And what is done is to apply a voltage at a given point on the boundary of the object. This voltage triggers a current inside the body. And then the corresponding intensity of the current is measured at the boundary of the object. And now, given the measurements of the intensity of the current at the boundary of the object, one wants to infer the internal structure of the object. And in mathematical terms, this problem is modeled through the Poisson equation, where the interior structure of the object is described through the conductivity of the medium. And then the inverse problem consists in finding the conductivity A, given measurements of the intensity of the current at the boundary, where the intensity of the current is nothing but the Neumann trace of the solution at the boundary. A similar example is optical imaging. And the difference with respect to, compared to the electrical impedance tomography is that in this case, the scan is done through light. And despite the similarity, the mathematical model describing this phenomenon is completely different, because here we have the radiative transport equation, and the inverse problem consists in finding the so-called scattering coefficient given measurements of the intensity of the radiation, which leaves the domain. But the main goal is the same. Given measurements of the solution or measurements of the observable at the boundary, infer the internal structure of the object, which can be modeled through the conductivity of the medium if we are talking about electrical impedance tomography, or the scattering coefficient if we are talking about optical imaging, but the idea is the same. And one similar example is also seismic, the seismic imaging. And what is done is to send waves in the ground from a source which is located at the top surface of the ground. These waves are reflected through different layers of the soil, and the corresponding pressure variation due to these reflected waves is measured at some receivers, which are again located at the top surface of the domain. And the inverse problem is to infer the velocity of the wave, which is a direct measure of the internal property of the object, given the measurements of the pressure variation at these receivers. So all these problems share a similar structure. For all these problems, we aim at reconstructing the interior properties of the object, given measurements which are taken only at the boundary. And the main issue of solving this problem is that measurements of the observable, which arise for a single instance of the boundary datum, do not suffice to infer the underlying coefficient that we are looking for. So to make it more clear, if we go back to the example of the electrical impedance tomography, if we set the voltage potential at this point, we measure the corresponding intensity of the current, and then given these measurements, which are realized for one single realization of the voltage, and we try to infer the conductivity even given these single measurements, then there is no hope to stably reconstruct the underlying coefficient. And actually, what is done for when solving these type of problems is to first apply a voltage potential at this point on the boundary of the domain and measure the corresponding intensity of the current, let's say psi1. Then move the source on another point of the boundary of the domain and obtain the corresponding intensity of the current, and keep doing these several times until we cover the entire boundary of the object through these sources here. And now, given the collections of these measurements, psi1, psi2, psi3, psi4, and so on, each of them obtained by different realizations of the boundary data G1, G2, G3, we try to reconstruct the coefficient. And now in this case, we can reconstruct the coefficient in a stable way. In more rigorous terms, for all these problems, the observable is actually an operator, in particular a boundary operator, namely an operator which takes as input a function which is defined on the boundary of the domain and returns a function which is still defined on the boundary of the domain. And now, if we consider the map which takes as input this operator and returns the underlying coefficient that we are interested in, then this map is unique and weakly stable. So now this underlying of this boundary operator, lambda A, is different for any of these problems, and it depends on the structure of the partial differential equation. But the idea is exactly the same. For all these problems, we can construct this map, which takes as input this operator and returns the underlying coefficient. For instance, In the case of the EIT, the boundary operator is the Dirichlet-to-Neumann map. For the optical imaging is the so-called albedo operator, the operator which takes as input the radiation which enters the domain and returns the radiation which leaves the domain. And for the seismic imaging, we have the source to receiver map. So again, for all these problems share a similar structure. And for all these problems, the map which takes as input a boundary operator, which can be different based on the nature of the PDE, and returns the coefficient of interest, this map is well posed, is at least unique and stable. And the main issue of solving these inverse problems is that they are very computationally expensive. And therefore, what we aim to do is to replace this inverse map with a surrogate deep learning data-driven model. But in order to construct this data-driven model, we need two main building pieces, namely a data and a model. So before going on, is there any question at this point? So we are addressing a class of inverse problems where the map from operator to functions, in particular boundary operator to function, is well posed. And now what we are trying to do is to approximate this inverse map through data-driven model. What we're going to do now is to specify how the data and the model should look like or might look like for this type of the supervised learning model task.
Roberto, this is Suku from Davis. I just had a question on the previous slide. When you impose essential boundary conditions at 2 points, say on the boundary top.
Sorry, you mean here?
Yeah, exactly. So what were the boundary conditions on the remaining part of the boundary? Is it zero flux or something?
Yeah, I mean, you can imagine a point source boundary conditions. Actually, when we run the experiments, for instance, we use some kind of wave type boundary conditions, which are defined on the entire boundary of the domain. And these are usually Dirichlet boundary conditions, at least for the electrical impedance tomography.
So but it's always okay.
Yeah, exactly. Yes. So you can imagine that it's let's say 1 at this point and 0 everywhere else. So just a function, for instance.
Like a hat function, right?
Yes, for instance. But this can be kind of arbitrary. And maybe it's going to get clear also once I talk about the data structure.
Yeah. Okay. Thanks.
Yeah, sure. You're welcome. Feel free to interrupt me at any point if you have any question. Okay.
Probably I can ask one more question quickly.
Yes.
Can you impose flux, like zero flux boundary conditions and knock off the constant which is in the null space by the average, because the average is going to be some number, right? So is it possible to do that?
Actually, also for this problem, also the Neumann to Dirichlet map, if you consider the operator which takes as input the Neumann data and returns the Dirichlet data, and the inverse map which takes this operator as input and returns the coefficient, this is also well posed. So you can also impose a flux function. Absolutely, yes.
I was thinking about, yes, exactly. I was thinking about the DTN map, basically. That's why.
Yes, absolutely.
Yeah,
you can consider either the DTN map or the NTD map.
Okay,
actually,
thanks.
NTD is even better because it's more stable than the DTN. Okay, so data. First, the first point is how to discretize this input operator, because now again we are trying to solve this supervised learning task where the input to the map is an operator. And actually, from what I told before, this should be already kind of clear. So one way of discretizing this operator is to consider the tuple of input and output functions, G1, Psi1, G2, Psi2, G3, Psi3, and so on. And those are nothing but realizations or samples from the underlying operator. So you apply a given boundary data G1, you obtain the corresponding observable Psi1, which is nothing but the action of the underlying operator on the corresponding boundary data. And then you repeat this process L times. And now a discretized version of our input operator is this collection of input and output functions, where again, the output functions are nothing but the actions of the operator on the input functions. And now if we assume that the operator is injective, we can kind of forget about the inputs. And we can only consider as a potential representation of the discrete operator just the collections of these output measurements psi L. So we have L, which is actually also pretty consistent with what is done in practice, because again, in practice, what you do is just to measure the observable, and then given the measurements of the observable, infer the underlying coefficient. But now, instead of having one measurements of the observable, we have L different measurements of the observable, each realized by different, for instance, locations of the boundary data. And now we move to the actual generation of the training data. So what we do, because of course the training of the model is done through synthetic data. So we generate ourselves the data in order to learn the underlying map. And what we do is to fix a given distribution over, or probability distribution over the input functions G, and we use the same, and we draw from this distribution L different functions GL, and we fix them. So now we consider an additional distribution mu A on the coefficients, and we draw at random a coefficient from this distribution. And now for each of these realizations of the Dirichlet data, we solve the underlying partial differential equation, which is in this case is the Darcy equation with the coefficient A and with boundary conditions G1, G2, G3, and so on. And then we compute the corresponding observables. In this case, the Neumann trace of the solution. And again, this operator simply arises from the nature of the partial differential equation. So we don't know exactly how to compute this, but this again comes from solving the PD. And now the tuple of L input L measurements psi L and coefficient A define one single data sample. And of course, now we can repeat this process with the same realizations of boundary data GL for n different realizations of the coefficients A. And then we put them together in order to construct the training data. So this is how the training data looks like. We have n samples defined by input, obtained as a collection of L functions, and output, which is a single function, the coefficient of interest. Okay, so is this clear? Because now we are going to move to the model part based on this construction of the data.
Yeah. So one quick question. This is Adar from Brown. How are you solving the forward part? Like you're using some Runge-Kutta?
No, because this is a time-independent problem. So we just use a linear solver.
Oh, you solve directly?
Yeah. I mean, we solve it directly in order to generate these training data. So these data are synthetically generated. So again, we consider differentiations of the boundary data. We draw a random different coefficients. For each of them, we solve the problems, and then we assemble these data. But the PD is solved numerically by finite differences, finite elements, standard numerical methods.
Oh, I was asking, like, which, because the follow-up question would be like, what's the order of that question? Because you have a lot of like surface waves and like a lot of phenomenons that you will get only if you solve it like high order, and then your finite differences of finite elements has to be high order.
No, actually, we use second order finite differences to solve these problems. We don't have extremely high frequencies for the boundary data.
Okay, cool. Thank you.
You're welcome.
Can I ask you a question also? This is
Yeah,
Nat Trash from
course.
Sandia National Labs. Can you comment on whether you imagine in the future that you would want to generalize to different geometries? Right. So right here you're working with the coefficients, but is there a way? Are you envisioning that as an extension in the future?
Yes, I mean, of course, it can be extended because after all, so for the time being, okay, so this is still the, let's say, the continuous version of the problem, at least in terms of functions, because now we have discretized the input operator, but still these psi L and these A are functions, and this can be defined on any arbitrary domain. The main issue is then on a discrete level, how to represent these functions. And so far we have considered only the case of Cartesian grid points or let's say points on circular domain, but also in that case you can kind of simplify to a Cartesian set of points in polar coordinates. But of course, then you can apply any type of data transformation prior, like you can kind of discretize these functions on a set of points that you wish. Then the only thing that matters is how you build the underlying model, because each model can deal with different data structures in terms of where you discretize the functions. So in principle, you can discretize it everywhere. And doesn't matter if it's a square, a circular domain, complex domain. But then, of course, you have to adapt the architecture in order to deal with this type of data. But yeah, I mean, there is a potential application to also other different domains.
Understood. Thanks.
You're welcome. Okay. Actually, also according to what I was saying before, now when it comes to the construction of the model, the learning model has to be consistent or has to respect the inherent properties of the problem or the task at hand. And in particular, what are the main properties that we would like the approximate model to satisfy? So first of all, the model that we are trying to approximate or to construct is a model which takes functions which are defined on the input and returns functions which are defined, input which are defined on the boundary, and returns functions which are defined in the interior domain. So boundary to interior. And now, a second and more important point, this inverse map is a map from operators to functions. And so what does it mean? I mean, what does it imply? First of all, we would like that at testing time, the model should be able to handle any arbitrary number of functions L tilde, discretizing the input operator. No matter if we have L functions, 2L functions, M functions, we would like the model to be able to handle, without retraining, any arbitrary number of functions. And we would like the model performance also to be independent of how many functions we chose to discretize our input operator. Or in other words, we would like the model to be independent of how we discretize input operator. And that's because, of course, if we imagine to deploy this model for practical for usage later on, then we might have given only let's say we might have given inputs, let's say measurements of the given observables, which are taken not in the exact same way we generate the training data. Maybe we generated the training data by using 10 functions, and then we are asked to compute the underlying coefficient at inference for maybe 10 measurements, because the practitioner has taken 10 measurements. And we would like the model to be independent of how many functions, how many measurements are taken. And so before delving into the specific architecture, a little overview about the so-called operator learning framework that probably many of you are already familiar with. So operator learning consists in functions to function map approximation. And here we are doing something slightly different, because now we are trying to approximate operators to functions map. And there are many widely used architectures. One very common architecture is DeepNet. And so DeepNet approximates, belongs to the class of operator networks, and it approximates the output functions as a linear combination of some basis functions tau with given coefficients beta, where the basis function tau depend only on the set of points where we would like to evaluate our output function, whereas the coefficients depend only on the input function f. And in standard practice, to approximate both the branch and the trunk, the coefficients of this expansion and the basis of these expansions with neural networks. And we call the branch net the network approximating the coefficient, and trunk net the network approximating the basis. And a nice property of DeepNet is that it can approximate functions, input and output function, let's say operators between functions which are defined on any arbitrary domain. So the domain of definition of the input function f and the output function h can be completely different. And this is actually very useful property for our purpose. However, DeepNet, as I mentioned before, it approximates operators, namely maps between functions and functions. So we need to modify modify a bit the architecture in order to be useful for our case. One additional architecture which is very used nowadays is Fourier neural operator. And this consists of the composition of different operators. First, the input function is lifted to an high-dimensional space through a linear transformation R. And then the output of this transformation is passed through a set of Fourier layers. And finally, is projected back to the original space through the projection Q. Actually, the details of the architectures are not relevant for the purpose of this presentation, but the main take-home messages concerning FNO is that this architecture, differently from DeepNet, is based on a non-linear reconstruction, and therefore it can be very expressive, in particular when it comes to discontinuous functions. And for our purpose, we might end up dealing with the discontinuous functions. For instance, if you imagine again the composition of the soil or the ground, this can be given by different layers, which can be represented by discontinuous functions. So we would like to have some expressive power when it comes to discontinuous functions. However, FNO can only approximate operators between functions which are defined on the same domain, at least the plain vanilla version of FNO. And also like Dupont, FNO approximates operator. So again, it's not completely useful for our purpose. So the architecture that we propose is called neural inverse operator. And now, based on the main properties that we would like the model to show, we will I will build upon on these points different elements of the architecture. So first of all, in order to address the first point, namely input and output, which are defined on different domains, while still keeping the expressive power of FNO, we combine together Dupont and FNO. So what you observe here, this one is the branch net of Dupont, and this is the trunk net of Dupont, and then we have a set of Fourier layers here. So the branch net takes as input the collections of the L functions. So this is one single data sample, and it constructs the coefficients of the linear expansion of Dupont. The trunk net takes as input the variable z, which corresponds to a discrete version of the interior domain. So in this case, just Cartesian grid points, discretizing the interior domain. So again, these functions are defined on the boundary, whereas z is a discrete representation of the interior domain. And the trunk net returns the basis of this expansion. And now these weights and bases are assembled together in order to construct these L different functions, which are now defined in the interior domain. So Dupont moved the reconstruct from the boundary data some latent variable which is defined in the interior domain. And now this set of functions are passed through the linear transformation R, which returns the variable, or again, a second latent variable H, which is then processed through a set of different Fourier layer. And now you can see here how this operation looks like. This is simply a weighted average of these functions f of L, each of its own weight, WL. And now what you can imagine this architecture doing is first, Dupont tries to construct the solution of the partial differential equation inside the domain, given the measurements taken at the boundary of the domain. And then what the Fourier layers and FNO, like this part of the architecture does, is to perform the inversion, given the solution of the PD in the domain, obtain the corresponding underlying coefficient. And the main issue of the architecture as it is right now is that this architecture, despite being able to approximate, despite being able to handle inputs and outputs which are defined on different domains, still we have the problem that at testing time, if we are given L+1 function, we wouldn't know what to do with the last functions. Maybe we assign to the first L the parameters WL, and then what do we do with the last one? We set maybe the parameters equal to 0. It's not clear and it's not extremely rigorous. So what we did in order to make the architecture able to handle any discretization of the input operator at testing time is to replace this weighted average through a simple empirical expectation. So we assign basically the same weight to all these functions f of L. And now at testing time, if we're given a different number of functions L tilde discretizing the input operator, what we need to do at this point is just to compute the expected, the empirical expectation of these functions f of L. So these solves the point 2a. So now we are able to handle at testing time any arbitrary number of functions. However, as this stands now, we have no guarantee that the architecture will perform equally well when we consider different number of functions. And the main objection that one can do is that now we are kind of losing information because we are replacing a weighted average with a global average, where we are assigning the same weight to every function. So somehow we lose some information. And the way we solve this problem is through so-called randomized batch. So this is an algorithmic trick. And what we do, and it works in this way. What we do, so this is how our training input looks like. We have, again, collection of L functions. In this case, we have 9 functions. So what we do at every training iteration is to draw at random an integer number between 1 and 9. And then we draw from this box of functions, let's say L at functions, where L at can be anything between 1 and 9. And then we feed the model with this collection of functions. And now there is no problem with feeding the model with this input because of how we built the architecture in the previous step. And then we repeat this process at every training iteration. So not at every epoch, but really at every time we call the model, we draw at random a different number of functions from this box, and then we feed the model with this new number of functions. So iteration 1, we have 5 functions. Iterations 2, we have 9 functions. Iteration n, we have 2, and so on. And now, of course, we don't have any smiling face here because, unfortunately, we don't have guarantees about the mathematical guarantees about this algorithm. So we can only test the effectiveness of the model through numerical experiments. But the heuristic is that, so if we consider this architecture, and if we imagine there exists a distribution over these functions f of L, which are the functions which DeepNet reconstructs, what you observe with the first this first architecture is always and only the empirical expectation of these functions. Instead, when you construct these sub-batches of the training inputs, the model is able to explore the entire probability distribution, because maybe at some point you get 2 samples. With 2 samples, you get a very bad estimate of the empirical expectation, which maybe is located at the very end tail of the distribution. And then by repeating this process n times, with n being very, very large, somehow the model observes the entire distribution over these functions. And so this is how you recover the information that you lose by replacing this weighted average with this global average. One additional way to perform this task maybe is, instead of providing as input to the Fourier layers only the empirical expectation, you compute different statistics of this distribution. You take the mean, the standard deviation, the minimum, the maximum, and so on. And then you provide as input to these Fourier layers all these statistics. This randomized batch is just a more efficient way of doing this in order to explore this distribution. Okay, so now,
excuse me, can I ask a question?
Yes.
Is I'm Kamal from Brown. Is the same model the Fourier DeepNet? I put the paper in the chart. Is it the same model?
I'm aware of this. Is the I think I'm aware of this paper. The initial architecture is the same. Yes. What they do is to combine Dupont and Fourier.
Yeah, I think figure 3.
Yeah, I think this is this architecture here, but
Yes,
their work came after this one.
okay. So this is came before the other one.
Yeah, this one came
Okay.
in already January.
But the architecture is same.
What they do is to construct, is to combine Dupont and FNO. I think they also use some U-net principle here at these Fourier layers.
Yes,
But yeah.
It looked like similar, so that's why I asked the question. Is it?
Yeah, it's totally legit, and yes, I mean the basic architecture is the same. Yeah.
Okay. Okay. Thank you.
Or it's very similar.
Yeah. Thank you.
You're welcome.
Yeah.
And is there any question concerning the model? Oh, okay. Okay, so then we can look at some numerical experiments. So we consider different benchmarks. For the electrical impedance tomography, we consider a set of data whose coefficients, which we are trying to infer, look like these, like similar to trigonometric functions. We have different frequencies up to 7, each with different amplitude and so on. And this is how the input operator looks like, or at least 3 discrete samples of this input operator. Second example we consider for the EIT is the one of heart and lungs. And the coefficients look like this. Actually, the dataset is obtained by perturbing this reference configuration for with adding some noise, and then solving the underlying problem again with the finite elements. And this is a very simplified model, even though it's widely used, of human body midsections. These ones are the lungs, and this one is the heart of humans. And this is how, again, the input looks like. Third example, detection of inclusions. We have scatterers from 1 to 4, which are spread in the domain. And these scatterers are all the same shape. And what we try to reconstruct is where these scatterers are located and how they look like. For the optical imaging, we consider a similar example to the one before, but in 1D. And now we consider different coefficients by varying the height of these scatterers, the width, the location, and so on. Whereas for seismic imaging, we consider the problem of the family of coefficients belonging to the curve family, just some curvilinear layer. That's what I meant by discontinuous functions. So you can see some discontinuities between different layers, and the Style-Bell family coefficient. So the first experiment that the first test that we ran is to compute the performance on a testing set whose input are discretized in exactly the same way as the training.
I'm sorry, can I roll back? I just want to understand, what do you mean by family of coefficients? Like the Style-Bell, what Style-Bell, curve-Bell, what are those? Just
this is
like
one,
you change.
Yeah, this is one sample from this family. And then you can have, maybe I have here one additional sample. You see, this is a second example for a second sample. So you can have the samples belonging to the family all share a similar property, which is these curvilinear layers corresponding to different layers of the ground. But it's just like a family of coefficients which belong It has been developed by Los Alamos National Lab. It's called OpenFYI, and it contains a huge set of data for seismic imaging, including style-vel and curve-vel.
Got it. Okay, so you have it. So you're not actually using different family of functions to create data, but you already have those input functions. You just plug them in, and
Actually, for all the previous examples, we had in-house codes for solving the
so
PE.
to create,
Instead,
for example, this curve, you're playing with the like you have some sort of linear combination of signs or something like that.
I mean, these datasets are already available on the website of the people who created the dataset. So we just took the data from them. In this
Yeah,
case,
that's what I'm saying. Like you take the inputs, then you run them through a
no.
solver.
Also the output are already provided by them.
Ah, wow. Okay.
Yeah. No, it's huge. Like they have a huge set of data for seismic
Fun
imaging.
times. Yeah.
Yeah, including input and output. So these ones are given by these are samples of this data set. Same
Cool.
this one.
Thank
They
you.
also have so-called flat vel. Instead of having curvilinear layers, they have linear layers, like flat layers. Even some inclusions in the soil, like you have some objects and you want to detect this object. There are many data sets for the seismic imaging, not
Gotcha.
for the others. For the others, we generate the data.
All right. Thank you.
You're welcome. Okay, so again, the first numerical experiments consist in testing the architecture on a set of testing data which are unseen and which share the same discretization for the inputs as the training. So the training is discretized with L functions, and also the testing inputs are discretized through this exact same number of functions, L. And here, I mean, we compared the architecture with standard, with some other baseline, including DeepNet and fully convolutional neural network. Neural inverse operator performs slightly better, but for instance, in the trigonometric functions, visually there is not much difference between NIO and fully convolutional network. Similar results also for the Erten-Langs phantom. NIO performs better, but visually also the other architecture perform pretty well. Here we see some difference, and it's where probably we also get this advantage compared to fully convolutional network, because in this case, this is the exact coefficient. This is the coefficient predicted by neural inverse operator, and this is the one predicted by fully convolutional network. And you see that this architecture completely missed these inner scatters, and probably that's what brings the error a bit up higher compared to neural inverse operator. For optical imaging, again, this is one test sample. This is a second test sample. We see for this one, visually similar performance among the models. For this one instead, fully convolutional networks a bit underestimates this height of the scatterers. And similarly for curve-vel, actually in this case, fully convolutional network, which is what this one is actually a pretty powerful architecture used for seismic imaging, which is called inversion net, and this belongs still, and it's also mentioned in the paper from OpenFYI, where they have this set of data. They use this inversion net as a model, and in this case, the performance is comparable for the curve-vel family, a bit lower for fully convolutional network. For style-vel, again, we observe a slightly better performance of neural inverse operator. But so the main, the second test that we ran was to test the performance of the architecture on a set of testing data which have a different discretization compared to the training data. So now the training data again the training inputs consist of an operator which is discretized through L functions, whereas the at testing time we test through an input with a set of test samples, so which are still unseen, and also the input operator is discretized through L tilde functions with L tilde smaller than L. And now here we plot the median test error versus the number of functions L tilde discretizing the input operator. And you observe that the blue line is a neural inverse operator, whereas the orange and the red ones are DiPoNet and fully convolutional network. And we observe that when we test on in a set or on testing samples which with those inputs are discretized in the same way as the training, then all the model performs fairly well. However, when we move even slightly, when we consider even a slightly different number of functions discretizing the input operator, now we observe that neural inverse operator is pretty stable. It performs equally well for any type of discretization, whereas the other two the performance of the other two architectures deteriorate immediately when we consider a different number of functions, and the results become even 10 times worse. And we have seen a similar pattern for the Artel-Lange problem for inclusions of the detections. And this proves, at least experimentally, again, we don't have rigorous guarantee, it proves at least experimentally that the architecture is independent of how many samples, or how many functions we choose to discretize our input operator. And we observe similar results also for optical imaging, seismic imaging, and so on. Now, one additional experiment, very similar to before, instead of testing the architecture on a set of input testing of input data defined by L tilde functions with L tilde smaller than L, which was the training one. Now we test the architecture with a set of test data whose input are discretized by using L tilde functions between 10 and 100. So less and also more functions compared to what we use for discretizing the input operator during the training. And you observe very similar behavior. So this is the typical V-shape pattern that we see when we have this type of non-invariant discretization, non-invariant discretization of the model. And now what we consider next is the so-called out-of-sample distribution, because so far we've always considered a set of testing data which are unseen during the training, but still belongs to the same distribution of the training data, which is common practice in machine learning. So if you consider curve or like the inclusions of the detections, during the training data we had 1 to 4 scatterers. During the testing inference, we also consider a set of testing samples, including from 1 to 4 scatterers. And now what we want to do is to check how the model performs when you change the underlying distribution of the testing data. So instead of considering, for instance, scatterers which are square, we consider scatterers which are circle, and see how the model performs when you change this distribution, when you slightly perturb or change this distribution. For instance, we consider in the case of the inclusion detections, instead of 1 to 4 scatterers, 5 scatterers, and the model has never seen 5 scatterers, and the performance are still pretty good. And similarly, instead of considering 1 to 4 scatterers with the same shape, we consider 1 to 4 scatterers with different shapes. And also in this case, the performance remains pretty good. Of course, it deteriorates because those are completely unseen out of distribution samples, but still the model performs very well. And also for the heart and lungs, instead of defining the testing data by perturbing a reference solution by 8% noise, we perturb by 12% noise. And in this case, the performance is exactly the same. And this is actually quite surprising because, as I mentioned initially, the inverse map is stable, but still is weakly stable. And actually, people in the field of inverse problems almost consider this type of weak or logarithmic stability almost equivalent to no stability at all. So it was quite surprising to see that despite the nature of the map, also by changing the underlying distribution, the model was performing fairly well without providing completely random prediction. And again, we don't have like a reason why this happens, but the heuristic is that by training the model, you kind of enforce some stronger form of stability of the architecture itself, because you kind of restrict the functions that the model can return to a specific class of functions. You will not get, by training the model on scatterers, something which looks like the art and lungs quantum, because of course the model has been trained on the specific task. And one additional example was ablation study. We wanted to see how the additional Fourier layers and a randomized batch impacts on the performance of the model, because after all, it might have also not brought to any improvement. And what we observe here is the blue line is neural inverse operator with the Fourier layers and the randomized batch algorithm. The purple one is a neural inverse operator without the randomized batch, and the light blue is a neural inverse operator without the Fourier layers. And you observe that for all the experiments, if we include both the Fourier layers and the randomized batch, the model performs way better compared to not having either one or the other. And this is for different discretization of the, again, input testing operator. So to conclude, because my initial claim was, okay, we are trying to approximate the underlying map, because the actual inverse problem, solving the actual inverse problem with traditional numerical methods is very expensive. Is this actually true? So what we did was to compare the performance of the model with the performance achieved with the traditional numerical methods. And you can see this one is the heart and lung coefficient reconstructed through a traditional scheme is way more blurred compared to what the model reconstructs. And also the computational time for obtaining these is around 2 hours, whereas the inference time, only the inference time for a neural inverse operator is 0.1 second. And this is actually not a property only of NIO, but all machine learning models perform equally well in terms of computational time as neural inverse operator. So it's more like if we can use machine learning to actually solve this inverse problem to fall in a lower computational time. We did the same also for the inclusions of the detections. And I would like to highlight that this sample is an out of distribution sample, because remember, the training data we trained the model with was defined by scatterers of all the same shape. Instead, here we consider a set of scatterers with different shape. And you can observe that NIO, even on these samples, which is smaller and never seen, it kind of sees that there is something going on, and it provides some more blurred around the object, whereas it captures very well the edges of these two, because these are similar size of the one that the model has seen. And again, this one, 2% error in 0.5 seconds, whereas with PD constraint optimization took 30 minutes for with a 10% error. Similar results also for seismic imaging. So where do we stand, and actually where we would like to go? So as you have probably noticed, we don't have at the moment any mathematical guarantee. And what we would be nice is to construct an upper bound on the error of a neural inverse operator, and to see how the discretization of the input operator impacts on the performance, how other features impacts, for instance, on the error. And also one additional generalization, one additional thing that we would like to work on is to improve the generalization performance of the model on these out of sample distribution. And so I think I would like now to stop, and thank you very much for your attention.
Thank you, Roberto.
And if you have any question, I would be happy to answer.
Okay, so let's wait for. Do we have questions for Roberto?
I feel like I've asked a lot, but I do am
No,
Go
please,
ahead.
interested in
I'm
kind
happy.
of. So I was wondering, can you go back a couple of slides to the images you showed of the different shapes of?
So this one?
Yes, exactly. So I'm looking at this and I'm thinking, so your scatterers are like blobs with one like high intensity point in the middle, right?
Yes.
So in terms of application of this study, do you really need this whole, like to reconstruct the whole image? The prediction should be a reconstruction of the whole thing, or would for example, just trying to figure out the location of the three scatterers, like XY coordinates?
It depends on the application, and also I mean, if
Yeah,
you,
that's what I'm interested, like in terms of application.
I think in medical imaging, you would like to reconstruct the entire image. And also because if you, so let's say, one way is also, as you mentioned, is to predict where they are located. However, in this case, you are assuming that you know how the coefficients look like. So when it comes to then coefficients where might have different form from what you guessed, then you would have no idea how to actually reconstruct the coefficient. You see what I mean? Instead, in this case, is completely unparametric, because it just reconstructs the image without any type of assumption on how the image should look like, any parameterization. You are not predicting the size of the scatterers and the location of the scatterers. So if you're given a different task, maybe you have, I don't know, you want to predict also the shape, then you wouldn't be able to do it if you constrain yourself to a given parameterization of the state that you're looking for.
Right.
Does it make sense?
I agree. That leads me to the next question, which is how robust it is to the geometries. Like how good, like if you have a non-convex geometry, or I don't know, some crazy, like a star-shaped geometry, will you be able to pick up those?
We don't know yet, but that's what we are working on at the moment.
Awesome.
Actually, yes.
Cool, thank you.
You're welcome.
I think Professor Erhard has some questions.
Sorry.
We can't hear you. Yeah, we can hear you now. Yes.
Okay. Yeah, thanks for this very nice talk. I have maybe a more fundamental question. So I was wondering if your approach is somehow independent of the type of PDE. So it seems that, I mean, you have 3 different types of PDEs, but somehow you didn't dive into the details. I mean, if you think about stability estimates, then the stability estimates are very different for each type of PDE. So
yeah.
is a method really independent of the type?
No. I mean, we trained each model for each benchmark and for each PDEs. So the models are agnostic with respect to the physics. So if your underlying problem is governed by radiative equation, and then you apply a model which has been trained, let's say, on data generated by solving Poisson equation, there is no hope that the model is going to provide you reasonable and accurate reconstruction, unless you incorporate in the model itself, either with the architecture or the loss, some information about the PDE itself. But this is a completely data-driven model. So the model is at the moment completely agnostic of the physics, and it sees an input and returns an output, no matter what is the PDE, the underlying PDE. Of course, if the underlying PDE is different compared to what you are trained on, then the model performance are going to be terrible.
Yeah, and maybe one small extra question. Maybe I missed it. Do you need the knowledge of the fundamental solution of the PDEs, or are you computing the fundamental solutions?
No. We are not computing fundamental solutions. We are not computing Green functions. We simply have we have a code which solves the underlying PDE. What we do is to assign the boundary data, solve the underlying PDE, and obtain the corresponding observable, given the problem at hand. So again, for Poisson equation, we assign the voltage, we compute current, but we don't assume anything about green functions, fundamental solutions, or anything.
Okay, thanks a lot.
Welcome.
I've got a question. I'm Suku again from Davis. So you mentioned about the problem being ill-posed. So from the boundary data, you can get different realizations of A of X, Y, right? So is it possible that for a given solution, you can construct actually two functions A of X, Y, which give the same solution, boundary data?
Oh,
so
sorry.
that will show that, yeah.
I see what, okay, so I should have been probably more clear. The problem is ill-posed when you consider a single set of measurements. So again, if you, or very few measurements. So if we go back here, so if you consider the EIT, you compute the intensity of the current for one single realization of the boundary condition, and then given these single measurements, you try to infer the coefficient, then the problem is ill-posed. But when you set it in the framework of operators to function, or namely, if you collect many different realizations of the intensity of the current, each obtained by different realization of this voltage, then the problem is stable, even though it's weakly stable.
Yeah, that's right, because you were showing many exact coefficients and then comparing it to what you obtained, right? So then that's what was not clear. Okay. Also, the second question is of many other questions that people are asking. So if you just have a triangular domain instead of, say, a square or a circle, can you still do what you're doing by just mapping the triangle to a square and proceeding, or? So
the main reason why we used Cartesian and square domains is that we used these Fourier layers. And in Fourier layers, what it is done is to compute the Fourier transform of the input, then to multiply by some learnable parameters, and then compute the inverse Fourier transform. And this Fourier transform is computed with the FFT algorithm. And to use FFT, you need to have Cartesian domains. So the way you can, so the one way to do it, if you have like triangular domain, So what you can do is you consider Z can be everything. Z can be a discrete version of the triangular domain. Some just sample picked at random. Then you do everything exactly. You do the same that we did before up to this point here. And now what one can do in order to still be able to use FNO or like these Fourier layers is to include an additional transformation which maps this triangular domain into a square domain, do all the reconstruction, and then map back to the triangular domain to obtain the coefficient on the triangular domain, or replace directly these Fourier layers.
Yeah, I was asking because, whenever you construct a map from say a triangle to a square, of course, the Jacobian will vanish at one point, right?
Yeah.
So does that cause an issue? Because if you can do that, then potentially, I think you could even do unstructured, domains, right?
I mean, the authors of the paper of FNO also proposed this GeoFNO, which does exactly this. And they even mapped airfoil domain to Cartesian domain, which are not topologically let's say equivalent, and they got some reasonable results. I don't know mathematically if I mean in practice it should be doable. I don't know if it makes completely sense from a rigorous mathematical perspective. That's I don't know.
Yeah, because I don't know what will happen to the Fourier coefficients when you have when the Jacobian is not
because I wouldn't know. Actually, I'm not able to answer on top of my head like this question. I had no idea. Also because in the end, like the parameters, I mean, you still compute these coefficients, but then you multiply them by these learnable parameters that you learn during training. So it's very difficult to say what's going to happen, because when it comes to training and machine learning, everything is very obscure. So
thanks.
Yeah.
Some data. Who proposed GFNO?
With the FNO group. No, we proposed it in the DeepNet FNO paper.
Exactly. It's in our paper. We proposed it before the
GFNO is there.
The GFNO is in the paper, fair comparison of 16 different benchmarks. So we could do it. We did both the DFNO for dimension inconsistency and also the geometry.
Okay, right.
Yeah.
Okay, right. That
so we try to help them. We try to help them.
Okay. Okay. All right. That came before. I see.
But, I was wondering if Umer, are you in the audience? Umer may have a question, but okay, no, maybe. Good discussion, some data. Maybe we can go to the next one. Very, very good discussion. Roberto, thank you for the nice talk.
Thank you. It was very great pleasure.
You can stay here for our second talk, actually, Roberto.
Okay.
Okay. So
thank you.
Maybe you can stop sharing, maybe?
Yes.
It's all European today. It's nice. It's nice. I like it.
Thanks again. And
ciao.
Bye.
Okay. So we move to our second speaker, a second presentation. It's a joint presentation by Professor José Antonio Font and his student Antonio Ferrer-Sánchez. So you may want to share the screen when I introduce you to the audience.
Sure.
So Professor Font is a full professor of astronomy and astrophysics in the University of Valencia in Spain. He has many years of experience in large-scale supercomputing application in relativistic astrophysics, in particular in the fields of numerical relativity and relativistic hydrodynamics, having co-authored over 250 articles in peer-reviewed journals. He is a member of the Spanish Royal Physical Society and the Spanish Astronomical Society. His student, Antonio, is a second-year PhD student in the same university. His primary research area is mainly focused on the development of deep learning applications applied to physics. His ongoing thesis focuses on the utilization of pins to address challenges to explore the boundaries of fundamental physics, in particular with the domains of astrophysics and astronomy. With that, please join me in welcoming both of them for today's presentation.
So
me
thank you very much, Sundata.
Thank you very much.
So as you were saying, this will be a joint presentation. I will start presenting the actual problem that we want to solve with pins, which are relativistic hydrodynamics, Riemann problems in relativistic hydrodynamics. And then later on, Tony Ferrer will talk about the actual method, the gradient-annihilated physics informed neural network method that he has developed. So this is, first of all, we would like to thank you for the invitation and for your interest in this work. So I hope you like our presentation. So this is a paper we have recently submitted, which is done by these 5 people here listed in the title. All of us belong to the University of Valencia in Spain. Okay, so let me see. It seems I cannot. Okay, there we go. Can you see my screen well? Can you hear me well as well?
Yes.
Okay, so this is the outline of the presentation. So basically, I will give a brief introduction and motivation to the physical problem we want to solve, which is relativistic hydrodynamics with physics in 4 neural networks. That would be my part, and then Tony's part would be the second part for the actual method, as I was saying, and the application to see how these spins actually perform to solve Riemann problems in relativistic hydrodynamics. So these are some of the keywords of the presentation. So the first keyword is Riemann problem. What is a Riemann problem? It's basically an initial value problem with discontinuous conditions. Then neural networks, for our choice would be a physics informed neural network. And then the physical application would be the Euler equations, but in the relativistic case, not the classical Euler equations of Newtonian hydrodynamics, but the Euler equations of relativistic hydrodynamics. All right, so as you all know, since they were proposed first in the seminal paper by Raisi, Perdikaris, and Karniadakis in 2019, nowadays physics in 4 neural networks have become as very widely used techniques to solve numerically partial differential equations based on machine learning. So these neural networks compute the solution of partial differential equations incorporating physical information, both in the architecture of the network and in the training procedure. So they learn from both the data and, most importantly, from the physical laws of the problem. And this second part is, in my opinion, what makes them very, very interesting for physical applications. So we know that partial differential equations, continuous partial differential equations, can be approximated or solved with neural networks. There is this theorem by the universal approximation theorem by Pincus that guarantees that in principle this is the case. However, if we have discontinuities or discontinuous solutions in the PDE, there is no theoretical background that ensures that the neural network is actually going to produce the correct result. And in the case of hydrodynamics in particular, we have this issue of since this is a nonlinear hyperbolic system, you are always going to be facing discontinuous solutions, even if the initial data is smooth, just because the equations are nonlinear. So we know how to solve hydrodynamics, nonlinear hyperbolic equations using finite volume methods, but this is not the point. The point of our study was to see if using pins, we can actually also solve those equations, because for finite volume methods, we have some issues when trying to solve those equations in the case of relativistic hydrodynamics that I will briefly mention in a minute. So let me tell you a little bit about what we are interested in solving, these relativistic hydrodynamics equations. They are obtained from local conservation laws. Local conservation laws of a tensor, the stress energy tensor, that has the content of the momentum, the momentum of the fluid and the energy of the fluid, and also the conservation law of the matter current density. If you see my pointer, these are those equations written here on the left of the screen. So this nabla mu is a covariant derivative associated with the 4-dimensional spacetime metric. And then the current density of the matter is given by this quantity J mu, which is the rest mass density of the fluid times the force velocity. So these indices here, the Greek indices, go from 0 to 3. Those are space-time indices. 0 is for time, and 1, 2, and 3 is for the spatial coordinates. And then T mu nu is the stress energy tensor, as I was saying, that typically for most application, people consider a perfect fluid. So the stress energy tensor of a perfect fluid is this quantity here, where we have also introduced this H, which is the enthalpy, and P, which is the thermal pressure. G mu is just a metric, the inverse metric. So now these covariant equations here have to be explicitly written in terms of a coordinate chart. And then once you select a coordinate chart, these equations transform into those equations here on the right, on the bottom right part of the slide. So this is a balanced law equation. These are 5 equations. So you have here the conservation laws of mass density, the conservation law of momentum, and the conservation law of the energy. It's not, strictly speaking, it's not a conservation law because you have terms on the right-hand side of the equations, but those terms do not depend on the state vector of the equation. They only depend on the metric. So if we were in a flat metric, in Minkowski metric, those terms on the right of the equations on the source terms would be exactly 0. But if we were in Cartesian coordinates, if we were in curvilinear coordinates, we will also have some geometrical sources. But you know, it's not much different to what we have already in the case of the Euler equations of Newtonian hydrodynamics, where in curvilinear coordinates you can also have this kind of geometrical sources. All right, so there are many formulations actually to solve those equations, and they depend on the choice of the slicing of the spacetimes, because the level surfaces of the time coordinate can be spatial or can be light-like or null. So the space-like hypersurfaces foliations is the most widely used in numerical relativity, and this is called the 3+1 formulation of relativity of the Einstein's equations and of the hydrodynamics as well. And the second choice that we have is the primitive variables, the physical variables with respect to which we will formulate the problem. So those physical variables are typically the rest mass density, the velocity of the fluid, the pressure, the enthalpy. But it turns out that in the case of the relativistic hydro equations, we have a different set of variables. Our conserved variables are not actually the physical variables. The state vector is a vector that is constructed from some basic primitive variables, and then this complicates a little bit the algebra when trying to solve those equations. So already back in the 70s, these equations were tried. People tried to solve those equations in full 3D, but they were formulated as a set of advection equations, and the price to pay by doing that was to move to the right-hand side terms that broke the conservative nature of the equations. And it turned out that by doing that, there were some limitations when solving the equations if the flows were had high speeds, the so-called relativistic regime with high Lorentz factors, let's say. And then conservative formulations, which share some ideas with the conservative formulations in the Newtonian case. Those conservative formulations for the relativistic equations were proposed in the 90s, and here you have some of the people that presented those formulations. So I will be briefly talking about the formulation of Banyuls et al., the third reference here, which is nowadays known in the community of numerical relativists as the Valencia formulation of the relativistic hydrodynamic equations. So,
sorry, I was going to ask a question about the last slide.
Sure.
Nat Draskett, Sandia. So for the right-hand side, the metric terms that appear, should we interpret those as being constant, or are they a function of the state? So like, is it a given manifold that you're solving on, or is it something that's evolving in response to the flow?
No. I mean, you could evolve them and you could not. That depends on the problem you want to solve. So for instance, if you're studying, say, a merger of two neutron stars, or if you're studying the collapse of a star, then the space-time metric is also evolving in time. And then in addition to these two equations, you have to solve Einstein's equations, which is the generalization of Poisson's equation for the gravitational field. But if the fluid is non-self-gravitating, then you can assume that the test fluid approximation is valid, and then those terms on the right-hand side are just functions of the coordinates, but they are constant in time.
Crystal clear. Thank you.
Okay, thank you. So as I was saying, this formulation that we proposed in the 90s shares many aspects with the Newtonian formulations of the Euler equations. We have a hyperbolic system. It is conservative, and then we can solve those equations using the same kind of Godunov type methods based on Riemann solvers to solve those equations using the characteristic speeds, the eigenvalues of the Jacobian matrices of the system, and the characteristic fields, the eigenvectors of the system. So the tools that we have for computational fluid dynamics were translated to relativistic hydrodynamics as well. And this is the preferred choice. This is the high resolution shock capturing schemes based on Riemann solvers, is what everyone in the community uses nowadays to solve those equations, also in the relativistic case. But this is not what we are going to talk about here. We're going to talk about how to solve those equations using pins. So let me skip this technical part. Let me just go to the system itself that you have here in this slide. So you have 5 equations. Those are the conservation of mass, momentum, and energy. In 3D, you have 5 equations. Then the capital U is the state vector, which are these 5 quantities. The capital D is the relativistic mass density, which is the rest mass density times this function W. This W is the Lorentz factor, which is defined here. So Lorentz factor of 1 means that the fluid is at rest. Lorentz factor of infinity means that the fluid is moving at the speed of light. Then the second term in the state vector, Sj, is the momentum relativistic density in each of the 3 spatial directions, J, and is given by this particular expression here. And the final term, tau, is the energy, the relativistic energy density, where we subtract the rest mass density, the capital D, in order to recover the Newtonian limit. This is just a technical point. Okay, and then we have the vector of fluxes and the vector of sources. Now, as I was saying before, this vector of sources only involves space-time quantities, also fluid quantities, but not derivatives of fluid quantities. So in that sense, it is a conservative system. Okay, so this is the system in full, I mean, expanding the expressions, what we have in the first square in the top, in full GR, in full general relativity. Then on the bottom left, we have the limit of those equations in the flat case without gravity. This is the space-time, the Minkowski space-time limit. And on the right-hand side at the bottom, we have the Newtonian limit of those Minkowskian equations, which are the familiar Euler equations for the continuity equation for the mass density, the momentum equation, the Euler equation, and the energy conservation equation at the bottom. So the equations that we will be solving with pins is the system in flat spacetime, in Minkowski spacetime. So the equations on the left bottom. And we will be solving them only in one spatial dimension, so in t and x. And we will be focusing on Riemann problems in order to apply our pins, because we have the exact solution of the Riemann problem, and that exact solution we can use as the ground truth to compare the performance of our method. Probably you all know what is a Riemann problem. It's an initial value problem with discontinuous initial data, and the solution is just basically constant states separated by waves, rarefaction waves, shock waves, and contact discontinuities. And this exact solution of the Riemann problem was obtained for the Euler equations of Newtonian hydrodynamics by Godunov in the 50s, at the end of the 50s, by considering a perfect fluid equation of a state, and this is used in order to compute the numerical fluxes of the finite volume method, of the high resolution shock capturing method. And this solution was extended in the 90s to relativistic hydrodynamics by these 2 authors, Martin and Muller. And this exact solution in the relativistic case is the one that we will be using as the ground truth, as I was telling you before. And why Riemann problems? Well, when you discretize a continuous solution, a continuous PDE on a finite grid, what you have is a family of local Riemann problems at each cell interface between your neighboring numerical cells. So if you know how to solve a Riemann problem, then you have piecewise constant data here in red, and then the solution of local Riemann problems at each cell interface gives you, in principle, a way to solve to advance in time the solution, the initial conditions. And this is what is plotted here on the left. We have on the second plot here, what we have are the different conditions for our waves, the shock wave. So for instance, in this interface here, we have that the pressure on the right is higher than the pressure on the left. So we will have a shock wave moving to the left, and then a contact discontinuity in between and a refraction fan on the right-hand side. And on the interface on the right will happen the opposite, because the pressure on the left is larger than the pressure on the right. So on the top, the image on the top, we have the exact solution of the pressure profile as a function at a given time as a function of the spatial coordinate x. And that solution at time tn plus 1 can be therefore obtained from explicitly using this kind of flux conservative hyperbolic method, flux conservative methods, which is fully explicit. And then we compute these numerical fluxes at the cell interfaces solving Riemann problems. So with pins, we are going to sidestep completely that. Well, before going to that, let me tell you, you probably know that these high resolution shock apnea schemes provide very stable and very accurate shock profiles, as I'm showing here, two different problems, a shock tube problem. The solid lines are the contact, the exact solution, and the symbols represent the numerical solutions obtained with a high resolution shock apnea scheme. And the problem on the left is a relativistic shock reflection, where we have a fluid with very high speed that bounces off a wall, and then a shock wave forms. And as you can see, these high resolution shock apnea schemes, even if for very high speed flows, they obtain the solutions very accurately. And the discontinuities are propagating at the correct speeds, and nonlinear features are very accurately resolved. So our goal, our objective is to try to see if pins can also reproduce these results and can achieve such good results as the more traditional high resolution shock apnea schemes in the presence of discontinuities and high speed flows. Because if we manage to do that, we will also be able to study some problems that are yet unsolved in the case of relativistic hydrodynamics, especially in more than one dimension. And we will also sidestep a technical difficulty of recovering the physical or the primitive variables from the conserved variables, which is not not given in closed form. So one has to do an iterative process in order to recover the primitive variables. And this is very time consuming. If we manage to obtain this level of accuracy using pins, then we will completely sidestep that particular step, the recovery of the primitive variables, and that would be very beneficial in terms of performance of the method. So this is the main motivation, and at this point I will stop, and Tony Ferrer will talk about the actual method that we have devised in order to solve those equations that I have just listed. And if I'm not mistaken, Tony is going to share the screen from now on.
Yeah, I'm going to share the screen.
Before you turn it over, can you comment on the electromagnetism version of this, right? Like coupling to Maxwell and so on, for shock magnetohydrodynamics, and whether you think that's viable with a pin and so on? Sure.
Yeah, that's actually a very good question. Yeah, so the GR hydro equations have also, the counterpart with magnetic fields, the GRMHD equations, they have also been obtained in flux conservative form as a fully hyperbolic system with, all the eigenvalues and the eigenvectors have been obtained. So high resolution shock apnea methods are being applied routinely to solve the GRMHD case as well. We haven't yet tried the GRMHD case, but this is something that we would like to do in the near future, because indeed it's a more extended problem, and certainly more interesting in many astrophysical applications. But in principle, it's also it's a system that in principle can also be attacked with the same kind of method that we are using currently to solve the case without magnetic fields. Indeed.
Excellent, thanks.
Mm-hmm.
So you should be able to see my screen at this moment.
Yes.
Yes, okay. So I will continue for a bit. I would like to start talking a little bit more about the motivation of the work. As Tony Font said, numerical algorithms may have some drawback when recovering the primitive variables, the density, the velocity, and the pressure, or the energy of the fluid, in terms of the conservative ones, the relativistic densities of mass, moment, and energy. So by using pins, this is a problem that pins doesn't care about, because we can demand the output of the neural network to be whatever we want, and this is one of the many advantages that we think that's on the pin side, because we can demand directly the output to be the set of primitive variables. So this is something that makes pins a good alternative, but obviously these kind of numerical algorithms, the high resolution schemes, have been studied in literature, and they have proven to give state-of-the-art solutions for this kind of problems. So the first step, the first motivation, was to check if a vanilla pin, baseline pin, is able to describe the discontinuities of this kind of Riemann problems, because in astrophysics it's of crucial importance, because we may have violent and extreme situations that usually lead to these discontinuities in time and space. So this, let's say, we have these both motivations. So I will just go a little bit faster here, because we just know how a pin works, but basically we use as input the time and the spatial dimension, because we are focusing on one-dimensional problems in the Minkowski spacetime, as Tony said. And basically we build this U tensor as the output. We will demand it to be the set of primitive variables, so we are able to directly get all the rest of all the conserved quantities, and therefore we can build all the equations and compute them with any kind of problem. So from this moment, we just build this F operator that's, well, it contains all the information of the underlying physics of the equations themselves. And we just basically build the loss function as usual by called the soft enforcement. We just consider the first term here is just the term that corresponds to the PD residuals. And here we can consider all the extra terms that the network needs to meet. For example, here we have the initial conditions, and we can consider any kind of experimental data, if there is any, of course, and the boundary conditions in space and so on. Basically, here we have all the physical extra information that the network needs to accomplish. So let's jump directly to the set of equations. As Tony said, this set of equations in the conservative form is the straightforward, let's say, modification of the classical Euler hydrodynamics. Well, we go directly to the space-time, Minkowski space-time, so we can consider fluids that have velocities around, well, very close to the speed of light, the ultra-relativistic cases. And when we consider this kind of scenarios, we need to use this set of equations. And, well, basically due to the fact of this Lorentz factor, the equations get, let's say, the variables get very, let's say, more coupled than the classical case. So this is the case, the reason that we don't have any way, let's say, analytical way to go from the set of conservative variables to the set of primitive variables. So this is a known drawback in the numerical, the high resolution schemes, where we have to do this this extra step for the recovery of the primitive variables in terms of the conservative ones, because we need them in order to follow with the numerical resolution. So this is something that with pins is something that we can avoid, because we just demand the output to be the set directly of the primitive variables, so we are able directly to compute the conservative variables, the relativistic density of mass, momentum, and energy, and then we can compute the equations with any kind of problem for that aspect. So going more into detail about the methodology we propose here is mainly based on two parts. The first part is something that have been stated in the literature, we can consider the activation functions in general of the hidden layers of the network, and of course of the output layers, let's say. We can consider them to be dynamic, understanding dynamic by trainable alongside with the loss function. In fact, in this reference, the authors get pretty well, let's say, results and state-of-the-art results in some equations that they propose there. And we thought that it could be a good option to implement for our PIN, because basically what we do is to understand this a slope parameter of the activation function in general as trainable, so we can get some kind of dynamic activation functions, such as here, for example, a hyperbolic tangent and the sigmoid function. What we do by increasing the slope parameter is we are stretching the activation function, so we are restricting the input values, the set of input values that have some information to backpropagate through the network. So this is something that may help the network to perform better in the description of the discontinuity. So this is something that we have considered. And the second approach, the second part of the methodology, is to basically introduce a new tensor, this called here this capital lambda tensor, that basically will depend in an inverse, well, proportionally inversely to the gradients of the physical variables. So we need this function, okay, to deactivate to a certain extent the loss function, and therefore we are deactivating a little bit, let's say, to a certain extent that will be measured with a new set of hyperparameters that will be introduced in a minute. And therefore, by doing this, we are forcing the network to basically not care a lot on the sample points that are in the discontinuity and in proximities of the discontinuity. And by doing this, basically the network doesn't try to interpolate in a smooth way the points that are around the discontinuity. So basically, the network is helped because we as we will see in the results section, this kind of modification helps the network to better describe the points around the discontinuity by just ignoring them to a certain extent. So let's say this deactivation is measured by a set of two new hyperparameters. This one of here, this alpha parameter, is basically the weight that's proportional to each one of the gradients of the physical variables, the set of primitive variables. And we can introduce also a new set of hyperparameters that is called here as beta. And they take the role of the different exponents of the physical gradients. So basically, we demand we can build several different functions with this definition. But basically, we want the function to be zero, that's it, to deactivate the network completely in the limit where the gradients tend to infinite. And on the contrary, we want the function to recover as a constant factor, so we can get the normal, the Manila loss function for the pin when the gradients are totally deactivated. So here we have plotted as just a matter of example the function 1 over 1 plus alpha times the absolute value of the of x in general to the power of beta. So we can directly see that by increasing the beta parameter that takes the role as the exponent, we will expect the pin performance to be some kind of, well, to get some kind of instability, because well, we are forcing more let's say the activation of the pin, okay, the annihilating, let's say, but we are in some where we can get some kind of instability, numerical instability, for some kind of problems, not for all, as we will see in the result section. But this is something that we could expect, and in fact, it happens. And okay, so basically, as a matter of example, here we have a diagram that basically is let's say a fully dense connected. as usual, when we work with pins, with the main modification here that, of course, we have these triangular slopes for each one of the hidden layers, and for the output, of course, we have 3 different activation functions in general. One for the velocity that has to be restricted in the range of -1 to 1, because we want to respect the underlying physics to not go higher than the speed of light, and the density and the pressure, okay, in general. So the main difference comes here in this redefinition of the loss that has to be with the PDS, the underlying equations. So to check the performance of the
question about your architecture. I think there's something I must be missing. So if you're not enforcing continuity, right, the idea is that that's the point of your capital lambda function. Then this, in a lot of ways, you must enforce flux continuity through like the Hugonio relations, right? This is the same thing as like in DG when you work with a broken polynomial space. You have to pay for it. Otherwise, you could have fields that kind of separate and lift apart from each other. So can you comment on that? That there is, you're kind of getting rid of continuity in the field, but you're not enforcing conservation anymore.
Yeah, we are. Yes, I think that I understand you. But basically, we use the same set of equations, but we modify the loss function because the loss function is basically let's say the heart of the problem, because we can use the same neural architecture for different set of problems in general. So we, by deactivating the neural network, we don't deactivate it totally. We just try to manage by using this set of hyperparameters. We try to deactivate it depending on the problem, because it's not always good for the result. This is something that you have to tune. But yes, we basically enforce the deactivation of the network in the special areas where we have high gradients, going to the limit where we have infinite, let's say, gradients, where we have we got the discontinuities.
In a collocation scheme, the role of continuity, it implicitly gives you the flux continuity, right? So if you're turning that off, you're going to need some sort of penalty somewhere in order to recoup that, right? So I suspect that even if you get good results by playing with the hyperparameters, there could be a poor initialization or something where the scheme will just break and lets you introduce a penalty or something that's going to bring that flux continuity back.
Yeah, that could be something that we could test, in fact, because yes, obviously by this modification, what we're doing is basically modify in certain manner the weighting of the true PDEs that are governing the system. But yes, what we accomplish by doing this is basically to force the network to not describe in a smooth way the points or the sampling points that are in the discontinuity and around the discontinuity. So in a certain manner, as we will see in the results, we get that the pin, this modification of the pin, is then able to see some jumps that the vanilla pin does not, and to enforce the resolution of the discontinuities. But yes, I agree with you that obviously this is still room for improvement, as we will take at the end of the presentation. But we think that the results that we get are in fact promising, and obviously there's still work to be done in that direction.
This is Suku here. Just to add quickly, just to make sure I understand what you're doing correctly. So essentially, you're trying to basically penalize, not penalize, basically wherever the gradients are very high, you basically don't want to basically make the weights very, very small so that you don't change it, basically, right? Is that the essence of?
Yes, more or less. Well, what we want to do is to weight more the part of the domain that is smooth, let's say, and we don't want the new work to focus on the description of the discontinuities, and by doing this, the new work is then able to solve in a better way the points that are around, or let's say that the points that are close to this continuity, but we need the new work to a certain extent to ignore the jump in the domain, because by having this discontinuity, we have a certain particular let's say, a point in the space that is not sampled. So the network, what it will do in general is to interpolate in a smooth way the solution between the points that are very close to from the left and from the right. So we then get this kind of interpolation, and and the limit of having an infinite training time, maybe we could get also a solution that's very close to the discontinuity. But by doing this, what we do is basically we try the new work to ignore the zones with high gradients. So we demand it to focus on the proximities and not to describe the discontinuities. So basically, the discontinuity is something that, to a certain extent, the PIN doesn't look at, doesn't pay attention at in some manner.
But in the first place, it must at least be able to find it. So once it finds a region of high gradients, then you don't penalize it further, basically. But of course, you must find it, at least you must find points where there are high gradients. Otherwise, it'll never, otherwise the gradient will always be large, right?
Yes, as we will see, in fact, in the result, that's something that when we vary this beta parameter here, the exponent, if we demand it to be so high, then the performance gets worse. In fact, because we need some kind of representation still in the discontinuity. But we want this is something that obviously this set of parameters we may think of some way to update them through the training procedure, but by fixing them, they become hyperparameters. So it's needed to find some tuning of them, because if we are so demanding with the new work, then we get worse results than the baseline model, and this is something that's interesting, and we will see in the results. So yes, basically, we propose 4 different problems in this field of the Riemann problems, 4 different scenarios. This is more or less the general configuration we use. We have the same neural architecture, 10 hidden layers, and 40 neurons for each one of the layers for all the problems. The same activation function, the T stands for the hyperbolic tangent, and in the output there's maybe some difference, because as I said before, we need the U, the velocity, to be bounded between the -1 and +1 in order to respect the physics. And we will be using also the soft plus function. That's let's say we have here some plotting. This is I think. Yes, this is the derivative of the soft plus function, and we have tested using different kind of set of activation function that, in fact, the soft plus function, as we will see in one of the problems, is better propagated through the new work, so maybe suitable for some problems, in particular for 2 of them, as we will see in the result sections. Basically, as a general configuration, apart from this, we use a leading rate of 10 to the -5 in order to ensure convergency, and a pretty well sampled domain in the let's say the inside of the domain, the space-time domain, and in the boundary, let's say we have just the boundary in time in the initial conditions. So we have 2 to the power of 15 points, but this is something that we could also play with and to find a point where we don't need to sample it more, because it's well sampled and the new work learns anyway the solution. In terms of comparing the performance of the vanilla PIN and our methodology, we use basically the relative L2 norm square. That we compare the prediction of the new work and the prediction of the vanilla of the baseline model, and of course the prediction of the high resolution schemes that Tony said explained before. For the last instant in time, that's it. That will change depending on the problem. But basically here we have used red squares to remark the best performance it's related into the lowest values for the L2 error. And I would like to note here this problem 2, as we will see in some slides, is the hardest problems that we have considered because we have exaggerated jump in the density variable. So here still the high resolution schemes are better, but our method is still better, only performs pretty better than the baseline model. And for the rest of the problems, we get always a performance that's comparable for the high resolution schemes, because high resolution schemes may be a suitable option when we work with one dimension in space. But when going to 2D and 3D, the problem gets harder because we need to do this process of recovering of the density, the pressure and the velocity variables. And maybe in that point, the pins may enter as a pretty good alternative, because some kind of problems are still not solved, and this is something that we can also investigate and to work with pins to check if we are able to extract this kind of solutions even with deep learning, even that they are not directly solved with numerical algorithms. So here in this plot we have 4 subfigures, one for each one of the scenarios that we have considered. We have plotted basically the L2 norm error in front of alpha. So when alpha is equal to beta and equal to 0, we get the baseline vanilla model of pins. That's plotted here with this dashed black line. This is the error of the vanilla pin for all the cases. We see, in fact, that, for example, for this problem, when we increase in general beta and alpha, we get better performance. But here, for example, as we were talking before, when we increase beta too much, so we are enforcing the network to deactivate too much in the areas with high gradients, then we can get some kind of numerical instability. And this is something that we could get, and that is needed we need to experiment on that aspect, because this kind of hyperparameters at the end, we have considered the same alpha and the same beta for the 3 variables. In general, they can be different, but in terms of make it easier, we just consider the same value. And for some problems, for example, this problem of here, we see that there's still some noise around the performance of the Bayesian model. This is a particular problem where we only have one discontinuity that's pretty easy to solve by a network. So our methodology is not needed, in fact, because a vanilla model solves them in a good way. But in general, when we have discontinuities, that we can get 2 discontinuities for the density, for example, and 1 for the velocity and another for the pressure, then the problem gets harder for a vanilla pin to solve. Here we have the first example that we have considered is the relativistic short tune problem. That's the same problem that we have in literature, but here in this case we are using velocities that are equal to half of the speed of light. So we are in a relativistic regime. Then we need to use the set of Minkowski equations that we saw before. Here on the top, for the 4 problems will be the same. On the top we have the solution blue dots for our approach, our pin. Here we have the same plots, but the prediction made for the vanilla pin. And represented in black, we have the ground solution, the known analytical solution. So as we can see, for example, here in the velocity, by ignoring the points that are around the discontinuity, that are very close to discontinuity, we are able to describe, obviously there's still room for improvement in some cases, but here, for example, in the velocity, it is clear how a vanilla pin tends to over smooth the corners, and by using this kind of the activation of the loss function, then we can describe it in a better way. So this case is, as I said, this problem is the hardest that we have considered, because we have here a discontinuity for the density that's pretty hard to solve by a vanilla pin. Here we are using the soft plus function. By using a sigmoid, we get similar results, but are not as good as this one we have here. That's why maybe the backpropagation of the soft plus function is better for this kind of problems. And obviously, even though the solution is not perfect, as we can check directly, for example, in the velocity and the pressure, the solution of a methodology outperforms by far what is the performance of a vanilla pin, because then our methodology is able to exactly detect where the discontinuity is and to ignore it to a certain extent. Therefore, we will focus basically on the dots that are strictly on the left and still on the right. So by ignoring the discontinuity, we are not predicting it. So basically, we are getting a better performance in that sense, because we are not forcing the network to solve them smoothly. In this case, this is the easiest problem, let's say, that where we only have one discontinuity, this one of here, and the other areas with high gradients are not really discontinuous, the discontinuities. So basically, in this case, we can use a baseline vanilla model pin, and then the solution is not bad, as we can see here. Obviously, well, when we use our methodology, we get maybe some epsilon of performance here around the corners. But in general, in this case, for example, where we have only one discontinuity, the rest of the variables are very, let's say, easy to solve by the pin. So the performance is more or less the same. But, well, we can also use our methodology because it's more, let's say, it can be some aspect, we can understand it as a generalization of the vanilla pin when we are working with discontinuities. And the last case we wanted to show is basically a reflection test. The solution is more or less the same, at least at a visual level. But it's true that as we will hear, the L2 norm is is lower for our methodology. So in fact, it is working, performing better. And it's basically because of these kind of predictions here around the corners, where we have here the over smoothing of the vanilla pin. It tends to over smooth these corners, and here we still get some kind of flatness prediction. But of course, if we go to velocities, to high velocities, when we tend to approach the speed of light, this kind of jumps get higher and harder to solve. So as I said, this is still room for improvement, and for the future work, as we will tell lately, is basically even more performance that can be achieved. Here, one of the last slides that we have, here we present two figures for each one of the problems in 3 dimensions. This is the loss that we are using, that's being weighted by this annihilation of the gradients. And here on the right, we have the loss for the vanilla pin. And the most important thing that I want to note here is that the initial condition is basically alongside with the loss function in terms of methodology, but physically, the initial conditions are the core of the problem. So if the initial conditions are not well described, then we cannot expect a very nice resolution for the next steps in time. So here, when using a vanilla pin, we can see that in general, the most amount of the error, the physical error, is bounded around the t equal to 0 around the initial instance of time, and by weighting the physical loss, what we accomplish, and we will check it by predicting just over t equal to 0, then the initial conditions are in general better described, and since the initial conditions, we don't have too much error there, we can more or less ensure that the propagation of the error will be minimal, except for some cases, such as here, for example, that we have a peak, but it's just can be considered just an outlier for a certain internal time, and we can just nothing too much about it. But in general, the error for time steps that are close to the initial time is reduced by a lot when using this kind of loss. And just in terms of ending, here we have plotted as a 2D heat map the lambda function that we get off of training. Here we have these blue zones are discontinuities for the 3 variables, and we can mix there can be some mixing with diffusion, let's say diffusion zones of the fluid. And when we got some green color, for example here, it means that this discontinuity is just for one of the variables, as we had here this problem. This corresponds to this discontinuity of here, just for the density, and the blue zones of this heat map will correspond to expansion zones where the gradients are big, but in comparison with the rest of the space-time, but we get some let's say gradual increasing of the gradient. So we expect that by naturally detecting where the discontinuities are and where the zones where we have the largest gradients, we expect the network to work well, the performance of the network to work better, to be better. And just to recap a bit what we said. Of course, when we are working with one-dimensional problems in astrophysics, using resolution schemes, high resolution schemes, numerical algorithms in general that are very well studied in the field can be a suitable option. But when we go to 2D and 3D, since we have this drawback in the Minkowskian equations, we have this drawback that we have not in the case of classical hydrodynamics. This is the fact that we cannot recover in an analytical way the primitive variables of the fluid in terms of the conservative ones. So we expect the PIN to be, in general, deep learning methods to be an alternative, a suitable alternative when we want to solve problems in 2 dimensions and in 3 dimensions in the space. And that's something that we want to test as a future work, of course. And it's very important for the field of astrophysics because we have some kind of problems in the astrophysics domain that are not solved, or at least they are not solved until we get the performance that we really want. So deep learning basic methodologies can enter into the field as a suitable alternative, and of course we will want to work on that direction and to improve our methodology and check if we are able to describe some new phenomena that's not being solved in astrophysics. And of course, something that we can do is to go to the ultra-relativistic regime, where we have initial conditions of the velocity that are very close to the velocity, or to the speed of light. So we need to learn very well in fact the velocities, because the final resolution in time will mainly depend on the initial values of the velocities in these ultra-relativistic domains. Something that we can work with is also, as Tony said, the source term of the equation, that for our equation is 0 because we are working in Minkowskian spacetime, so we have no curvature. And a direct extension of the work by using this kind of methodologies will be to, for example, consider an arbitrary, let's say, metric in spacetime. So we got these kind of new terms, and then we can check if a methodology based on the learning is still able to solve them properly. And of course, a possible extension of the work is to go, as I said, to 2D and 3D problems, and then we are able, for using the same kind of architecture, of our architecture, we are able to solve different problems. We can solve problems in in the classical domain, in the relativistic domain with no curvature. We can enforce the spacetime to have some Riemann tensor of curvature. Then using the same architecture, just by enforcing the different physical constraints through how the loss function, we are able, using the same, let's say, basic methodology, we are able to extract the information and to simulate different problems in the astrophysics field that can be in general of different nature. So that is more or less everything that we wanted to talk about. And thanks for attending, and I hope that this meeting has been useful for you all. Thanks. So you have any kind of question?
Thank you, Antonio, and thank you, Stefan. Do we have questions for our speakers? Professor Sukumar, you wanted to ask some questions? Just unmuted.
Hi, I just wanted to know in terms of the hyperparameters, or even I mean, if you change the width and depth of the network, and or what are the things you have to, how robust is it, right? I mean, in terms of you've shown.
Yeah.
So what are the plus and minuses, I would say, right?
In all the scenarios that we have considered, we just take alpha equal to beta equal to 1 because we can, this set of hyperparameters in general, as they are defined, they can be different. We can get some alpha rho, alpha u, and alpha p, so we can get different values. Yes. So as they are hyperparameters, so if we enforce them to be constant from the beginning of the training, we should make some kind of a study more into detail, such as this, where we can more or less calibrate, let's say. But in this case, we have the analytical solution, and it's more or less easy. We can say that. But in the case we don't have any analytical solution, we may think of a way of somehow updating this set of parameters through the training process. Or maybe we can consider them to be trainable throughout the training process. So the main the optimizer by itself detects which is the best way of updating them through the training. So, but let's say that the numerical instability, since these kind of equations are very sensitive to initial conditions. Just for example, for the Lorentz factor, that's one of the reasons. We expect, and that has been proven, that by this exponent of here, we cannot consider it. Of course, we just can get the alpha parameter but by considering this set of beta parameters, we're able to get some more flexibility. But we expect the instability, and in fact, that's what happens. The stability in the numerical resolution mainly comes in general when we increase too much the value of beta. So when we enforce the network to deactivate too much, in fact, the network needs to still get some information of the discontinuity and of course, around the discontinuity. But yes, for example, in this case, by increasing the beta parameter, we expect to get better results. This in red here, pretty better results. In fact, more or less half of an order of magnitude in the L2 norm. But yes, of course, there are hyperparameters, and we need to do some calibrating before the training. But more or less, alpha equal to beta equal to 1. It sounds to be not too aggressive, a modification not too aggressive of the vanilla pin. So that's what we use in the scenarios.
What about the width and depth? You just fix it and leave it as what you picked initially, showed initially, or have you tried increasing the depth, for example, or is it robust, or does it change dramatically or not?
Do you mean the new architecture, right?
Yeah, right.
Yeah, yes. In this, for other problems, we consider the same new architecture. We have tested several configurations because maybe 10 hidden layers is probably enough and too much in some cases. But as we have some GPU power, we can consider a big network. But we have been doing some tests by decreasing the size of the neural network, and we don't see any. Let's say we see some good robustness. Obviously, if we decrease too much the depth of the neural network, maybe we arrive at a point where we need more weights for the problem to be fully described. But in fact, since we are working with equations that are not very easy from a mathematical point of view. And of course, if we go to equations in the general relativity regime, we will expect to not get problems from the architecture network. So we put tons of, let's say, not tons, but in this case, just 10 hidden layers, and we expect that we can forget more or less about this aspect and just focus on the loss function, because in the loss function we have all the physical information, let's say. Of course, there are some problems. For example, we can get some scenarios of initial conditions where, for example, the pressure variable may be so difficult, maybe harder to solve than the others, and therefore in that kind of situations we may need to split the fully dense connecting layer into two, let's say, two different legs. For example, we can consider one leg explicitly to use this kind of weights just for the pressure variables, and then we use a separate set of weights for the rest of variables. So that these problems that we are working with here, we don't need to worry a lot about the architecture, the new architecture, because it's more or less robust. And yeah.
Also, I think one more point might be that, I don't know if you can explore in your context.
Sorry, I'm hearing you a little bad, I guess.
The voice got bad.
Is it just me or is
All of us.
No, we can.
okay. Okay.
Might not be very.
I think there's some connection issue.
Yes.
It's
Yes.
okay.
Something that happens, I guess.
Professor, can you hear us?
Maybe he got disconnected.
Yeah.
Oh, I got disconnected.
Yes.
I'm off my phone actually.
Yes.
Do you want to ask him the question that you had? Does anyone have more questions for Antonio?
That's okay.
Okay.
Okay. Okay.
Okay. I think Chris Zhao had a question. I think that already got answered with what Professor Kumar asked. Do you have more questions, Chris? Probably got disconnected also. So thank you, Professor Font, and thank you, Antonio, for taking your time out and giving us this presentation today.
Thank you so much for the invitation.
Thank you so much.
So we would be actually uploading the recording of today's presentation on our YouTube channel. So please feel free to follow us over there. Thank you, everyone, for tuning in, and have a great weekend ahead.
Thank you.
The same for you. Thanks.
Bye.
Goodbye.